start recording. Okay. Now that everything's all set up, I'm just gonna hit refresh on this real quick. I'll move that down there. Make sure there are no other requests. I should check the other two. No, those are old. I'm gonna make sure nobody posted new things there. Okay. Nope, those are from last week. So the only request was from Wyatt to look at homework 15, problem 3. And Wyatt says, I think my issue is coming from the conversion of Cartesian to polar, but I am going to work through the whole thing because I don't have like half of it worked out ahead of time. So, and then when we get to that conversion, I'll slow down and see if there's anything about that process that's causing issues. Okay, so the problem is to find the surface area of z equal x squared plus y squared inside x squared plus y squared equals 16. And the hint is to convert to polar after setting up the integral. One problem that a lot of people have had with this problem is figuring out what part goes into surface area and what part goes into the region R that we integrate over. So our surface area formula is going to be an integral over some 2D region R of root 1 plus fx squared plus fy squared dA. And in this case, for us, f is going to be that x squared plus y squared. It's the thing we want to find the surface area of. And R is going to be coming from the region we're considering the surface area over or inside that circle, x squared plus y squared equals 16. And WebWork calls that a cylinder because a circle expanded into a third dimension is going to be a cylinder. So for f equal x squared plus y squared, we know that fx will be 2x and fy will be 2y, just taking our partial derivatives. So what we're going to have is a double integral of root 1 plus 2x squared plus 2y squared dA. And then that's going to be a double integral of root 1 plus 4x squared plus 4y squared dA. The other thing that I saw a little bit of in class was just forgetting to square that 2 along with the x. So some people ended up with 2x squared, 2y squared. Just make sure that square hits everything inside that term. And then if we wanted to set up this region, it would help to draw it. So the region R is coming from this shape. I guess you're told it's a cylinder, so it's actually this shape, like this, with radius 4. And then the paraboloid is kind of this bowl shape. So what we're actually finding is this surface area that kind of sits inside the cylinder. But when we do the surface area formula, we think about the region projected down into the xy plane. So that's why I drew only 2D to start. I'm going to go back to that now, eventually. Okay, so thinking about projecting that cylinder shape or that section of the paraboloid that we're thinking about the surface area of, that's actually going to be this circle. Again, with radius 4, that's x squared plus y squared equals 4 squared, which is 16. And so we have this object that we're finding the surface area of, and this base of it is going to be the same as that circle. which I'll go ahead and leave that there. It's not hurting anything. Okay. So if we were thinking about this in Cartesian coordinates, which is the first thing we learned, so a lot of people jump to it right away. You get that the top part of this curve is root 16 minus x squared, and the bottom part of this curve is minus 16 minus x squared. So bottom to top bounds and y like that. And then left to right, you could find out that this interval is given by -4 to +4. If you didn't reason through that by the fact that this is a circle, and so its furthest distance everywhere is 4, you could also get that by setting your two bounds equal to each other. Since it's something is equal to its negative, that means that the thing has to be 0, which would get you x's plus or minus 4. But if you set that up, it turns out that it's really hard to evaluate it that way. And so what we actually prefer to do is to evaluate this one in polar coordinates. And that's the hint that's given to us, but if you weren't given the hint, you might start doing this and then realize that's a whole mess. Instead, a circle is gonna take on bounds theta from 0 to 2 pi. So we start here and we spin all the way around. So we get 0 to 2 pi. And then our radius is going to be 0 to 4. So the area starts at the origin and then goes all the way out to radius 4. So that 0 comes from this circle doesn't have a hollow part to it. It goes all the way into r equals 0, hitting the origin. And the limit 4 comes from that this circle had radius 4 to start. I guess one common way to get this wrong would be to forget to take the square and instead have 16 as what you think the upper bound for the radius is. And then in order to evaluate this in polar coordinates, we also have to convert the thing that's inside the integral to be in polar. So since we have a 4 times the x squared and times the y squared, we can factor that out separate. And then we can remember that x squared plus y squared is r squared. So we would just get that thing inside the integral is root 1 plus 4r squared. You can also do this by taking x equals r cosine theta, y equal r sine theta. And I may have those swapped. Please go by what's in your notes, not what I said just now. But you can plug those in directly and square them, and then remember that cosine squared theta plus sine squared theta is equal to 1 to get rid of the theta. So if you forget this substitution, you can get the correct answer using the direct substitution of x and y separately. It's just a little bit harder. So if you remember x squared plus y squared equals r squared, it just goes a bit faster for you. So our integral, once we plug in all the changes, is 0 to 2 pi, 0 to 4, just for my bounds for theta and r that we found on the previous page. And then 1 plus 4r squared, replacing that surface area formula. And then dA becomes r dr d theta. We just have to remember to have that extra r when we convert dA to polar coordinates. And then from here, it's just evaluating the integral, which I'll do in a second, but I want to check in real quick. Wyatt, I know you said that converting it might be the problem. Do you have any questions getting up to this point? Okay, cool. then I'll go ahead and evaluate it from here. So since there's a funny thing inside a square root, this looks challenging to integrate. Whenever you have like powered terms inside a square root, a trig function, or an exponential, your first thought should be, maybe I can get rid of that using a u sub. So if I had u equal to 1 plus 4r squared, then I would have a square root u inside, which I can evaluate, unlike square root 1 plus 4r squared. In that case, du would be 8r dr, just taking that derivative. And there's an r dr right here already, so I could go ahead and replace r dr with du over 8. I rearranged this formula to look like this thing that I want to replace. And then whenever I do a u substitution, I have to change my bounds at the start or remember to replace at the end. I prefer to do at the start. Everyone has their own preference though. But 0 is going to become 1 plus 4 times 0 squared, which is 1. And 4 is going to become 1 plus 4 times 4 squared, which is, I guess I gotta Google what 4 cubed is. It's 64. So this is going to be 65. 64 plus 1. So then my bounds change to 1 to 65. And since I did this replacement at the start, I don't have to worry about swapping my variable back at the end. And this was only a substitution in r, so my theta bounds stay the same. So then this is going to be 0 to 2 pi. I'm going to pull out this 1/8 out front. Just to make my integral look easier. And I'm actually even going to say square root u is u to the 1/2. I know I'm going to use a power rule and it's easier for me to see it that way. And then when I integrate, I go up 1, so 1/2 plus 2/2 gives me 3/2. And then I have to multiply by the inverse, or divide by the new power. And I'm going to evaluate that from 1 to 65. And if I was unsure about whether this went right, I could check 2/3 times the power I'm at. I'm going to get rid of all the constants that I created, and that's going to be u to 1/2 if I take the derivatives, so I know I took the antiderivative correctly. So that's 0 to 2 pi. I'm going to combine those fractions. And then it's 65 to the 3/2 minus 1 to the 3/2, substituting in those bounds, d theta. And 2 over 8 is going to simplify to 1 over 4, so this thing is actually just 1 over 12. And I don't know what 65 to the 3/2 is. When I have to plug it into WebWork, I'll just leave it that way. But all those things are numbers, so they can just come out front. And then I'm left with just that d theta back inside. So integrating d theta gives me theta back out of it. And I would actually have 2 pi minus 0, but the minus 0 goes away, and so I just have times 2 pi there. That was 1/12. I dropped off the 1. And that would be my answer. And I could try to simplify it more, but the advice that I've been trying to give you all in class, especially thinking about taking an exam tomorrow, is that don't do any simplification you don't have to. It's a waste of your time and it's a chance to make mistakes. And also when you're doing web work, it simplifies for you. So if you make a mistake on simplifying and it marks it wrong, that can be confusing when the only thing that went wrong was a little bit of algebra. So I would just take this whole thing and try to plug it in. Wyatt, do you have any questions about this problem? Okay, cool. I'm gonna check real quick, see if anybody posted other stuff. If you have other questions, let me know in the chat, Wyatt. Otherwise, okay, cool. I'm glad it helped. And it looks like there aren't other questions and nobody else around. So if you don't have anything, Wyatt, I'm gonna end the call and upload this video, and then you can look at it later if you still haven't finished the problem. Was there anything else before I go? Okay, cool. Have a good one then.